Okay. Yeah. Thank you for inviting me. So my name is John McCormack. I direct a research lab at Monash University called Sensi Lab. I'll just very quickly plug that. It's an interdisciplinary lab set up to do data visualization. We work with lots of advanced technologies. We do lots of hacking. We have Raspberry Pis and Arduinos and all that kind of thing. We have lots of we have time to make fun videos with robots and things, so you can watch the video. There's some of the people who work there, very interesting. Okay, so I'm going to talk about my work, which I've been doing for a long time, and just give you a sense of some of the ideas that have influenced me and how I go about making the works that I do, and just to show you some in a fairly quick tour because we don't have that much time. I thought I'd start with this. This book. Probably everyone has those moments in your life where something happens, you get inspired, you read something, you do something, and that changes everything you thought about what you wanted to do. So when I was quite young, I happened to be fortunate enough to be in the US, and I went to this little conference called SIGGRAPH. I don't know if anyone's heard of that before. It's a conference on computer graphics in the United States. There's SIGGRAPH Asia as well now, which runs in basically more closer to our part of the world every year. Anyway, I went to the one in 1987, and part of the conference was that they had these courses, and I happened to just see this course that was called The Modelling of Natural Phenomena, and I thought, that sounds interesting, I'll go on to that. And it was completely mind-blowing in 1987, probably by today's standards, really boring, but in 1987, it was absolutely mind-blowing. There were just this group of people who were doing this stuff that back then was, to my mind, incredible. And it was led by this guy called Alan Fournier, who was a Canadian researcher, and he coined this term called database amplification. And I just quoted from the book. I just pulled it out of my bookshelf a couple of days ago. I took a picture of it because I've kept it after all these years because it was so personally influential to me. It refers to a group of techniques where the original model is rather compact, but it allows to generate large amounts of geometric or display primitives. And that just sounds kind of, okay, well, that's interesting, but what does that really mean? Well, part of the course that he ran talked about this book by D'Arcy Thompson called On Growth and Form. So D'Arcy Thompson was sort of a polymath biologist, and he wrote a book at the turn of the 20th century called On Growth and Form. And what was amazing about this book was that up until that time, most biology had looked at biology from the point of view of the perspective of taxonomy, classification, function, those kinds of things. What he did was just basically look at biological form and say, how did all this variation in biological form come about? And a lot of these ideas turned out to be wrong. So he published a revised edition, which is the one that I've shown here in the 50s. Late 1940s, I think it came out, maybe early 1930s. But it's a fascinating book to read. It was way ahead of its time. He was genuinely a Renaissance person. He sort of quotes poetry in there, but he was doing serious science as well. And I guess the modern day equivalent of that is Philip Ball, who was for a while the editor of Nature. And he wrote this book called The Self-Made Tapestry, which is very much inspired by On Growth and Form. So these books have been incredibly influential in the work that I've done. So just to tell you a little bit about the influences and then to show you some of my work. I've always been fascinated by nature and by biology, but I've never really, at high school I studied biology, but I never wanted to be a biologist, but I just really was fascinated by nature, and particularly the way that nature allowed this incredible diversity of amazing form to arise through a process that was what's referred to, biologists and philosophers refer to as non-teleological. That means that it doesn't have a direction or purpose. And without turning this into a big philosophy lecture, if you read philosophers like Daniel Dennett, who wrote a great book on this, or Richard Dawkins is another person who's written a lot about this, evolution is really often very misunderstood, but it's also incredibly profound, not just for biology, but for a whole lot of ways of thinking. So Daniel Dennett calls it a universal acid. It's like the blood that the alien spits out that just eats through everything. So all of the preconceived ideas that people had up until the advent of Darwinism were completely sort of eaten away by this incredible theory. Anyway, and another book that Richard Dawkins, or one book that Richard Dawkins wrote was called The Blind Watchmaker, and I remember reading this, and coincidentally this came out at about the same time as this modelling of natural phenomena course, and as part of that book, he wrote this very simple program called the Biomorph Generator. And what it does is very simple. It's just a pattern-making piece of software, but it mimics the process of biological evolution in a very simplistic sense. So the numbers that you see on the top here are the equivalent of digital genes. They're just numbers between two limits. And by changing the numbers, you change the shape of the form that gets generated by converting these numbers into some simple line drawing. But what's interesting about this is that each of these is controlled by these genes. But if I asked you to make a shape by just changing the numbers, everyone would find it almost impossible to make anything that looked at all sensible or interesting or useful. But what he showed was that simply by selecting a parent and slightly randomly changing each of the genes, you could get things that looked like the parent but were all slightly different. And then by bringing them together, you could get offspring that had characteristics of the parent but were still different, which is pretty much the way that evolution works. And I mean, if you read the book, he thought this was amazing. When he first wrote this program, he said that nothing in my biologist's intuition, nothing in my 20 years experience of programming computers, and nothing in my wildest dreams prepared me for what actually emerged on the screen. So when I read this, I thought, wow, if I could do something like this, that would be amazing, because he's been programming for 20 years and he's a biologist, and he wasn't prepared for what happened. I mean, when you look at it now, you think, maybe he needed to get out a bit more, or maybe his wildest dreams weren't that wild. But what was so fascinating about this program was that he was able to evolve all these shapes that look like trees or insects or fish, and he was able to do that without a knowledge or understanding of how to encode the genes to do that. He did that simply by selecting ones that looked even just slightly like a tree or a fish, and then just iterating through this process until he came up with things that looked really like trees or fish or so on. So what he was able to do was actually to solve a problem that people had thought about for years and years. It goes back at least to the French philosopher René Descartes, who basically said in modern parlance that no design can exceed the knowledge and imagination of the designer. But he was able to design things that he didn't know how to control or didn't know how to conceptualize, which again for me was like, wow, this is mind-blowing. At the same time, there was an artist called William Latham, who I'm still in quite regular contact with today, who was doing this process, but by hand. So he was an artist, he was working at the Royal College of Art, and he would take a particular form, mutate it, have a whole lot of offspring, select the one that he liked, and then basically apply the same evolutionary algorithm by hand. And he came up with these incredibly complex tree of life drawings, where he created forms through a mechanical process, not an artistic process, through a mechanical process, that were, in a sense, beyond his imagination. So about the same time, I was writing software, and I wrote this program, which still actually runs today, which is quite amazing. It was written in C and C++, and it ran on a Silicon graphics machine at the time, but it mimicked this process, but using a system called L systems. So these were invented by a Hungarian biologist, Lindenmayer, who was interested in modelling cellular development for mathematical purposes. It turned out that they're actually really good at modelling complex generative structures. So here's I know you can't read this, it doesn't matter, but basically it's like a programming language that I wrote, so I had to write a programming language. The programming language is pretty cryptic. In fact, it's so cryptic that even I don't understand it completely, but that doesn't matter because I don't actually write things in the programming language. The computer evolves things in this language, and then I can look at the language after it's evolved. So in just one page of code, it actually generates this model. So this is not modeled by hand at all. It's just all done through a code generation process, and you get this incredible detail and complexity, in a sense, for free. And I thought this was, at the time when I was doing it, I thought it was pretty amazing that you could write software that could do things beyond your imagination, that could exceed your limits as an artist or a designer. So I published a book in 2004 called Impossible Nature. You can still get it online, I think, today. But the artistic impetus for this work was really to think about what technology might be able to offer if it wasn't just about problem solving or being for a purpose. So what other reasons could you use technology for? Because technology is largely driven by engineering disciplines. Engineers are by nature problem solvers. And that's great because there are lots of problems that need solving. And also, software as a modern technology is something that always has a purpose. You write a program for a purpose. But I was really interested in the idea of what if we were to make systems with technology that weren't to solve a problem or weren't to have a purpose? Where would that lead us? Hopefully this narrative will emerge as I show you some of the works. This was a commission done for a billboard in Queensland. These are all evolved plants. This is the billboard. The plants were basically, I took simple models for the species of plants that used to exist in the area. There's a big freeway. It's in it's near QUT. There's a big freeway in there. 100,000 cars go past every day. In order for them to put the freeway there, they had to kill or remove all of the flora and fauna that was there. So I found lots of the old flora that used to be there and basically put them through this software and evolved these new and exotic forms that still somehow reminded you of the original plants that used to be there but were otherworldly and strange. The story that's I always like to tell about this work is that once this billboard went up, for some strange reason they put my name on there, so people would Google my name and send me emails and say, you're a fantastic artist, where did you learn to paint like that? And I had to reply back and say, well, actually I can't paint, a computer actually made all these images, and usually the reaction is very negative. But how can you call this art when a computer's doing it and there was no human involved in actually creating the imagery? But for me, that was the whole reason for doing it in the first place, was to say, how can I use technology to do something that exceeds my imagination, that is out of my control, in a sense. I've been working in this area for a long time, and these are just images from various exhibitions. I'll talk briefly about a more recent work that I did a couple of years ago. I was lucky enough to work at the Ars Electronica Centre in Linz, in Austria. It's a big sort of art and technology museum and research lab that's funded by the local Linz government and the surrounding government. And it's probably one of the major centres for art and technology in the world. Anyway, I was lucky enough to work there for a while, and as a visiting artist, and I developed this work, which was based on the idea of oil. This is a very famous photo from the 1960s, and it really shows how the human landscape has changed because of oil, not just because there are oil petrol stations everywhere, but just because so much of our built environment is built around this energy source that we've discovered. And also, if you look at the logos that come from oil companies, they're often very referential from where oil actually does come from. So, in a nutshell, fossil fuels, as the name suggests, come from fossilised microorganisms that a very long time ago were compressed in the earth and fossilised, and all of the energy that they gathered from the sun was basically encapsulated in them, and now we just dig them out of the ground as things like oil and gas, and we burn them, and that causes a whole lot of problems. That's probably aware of. But the logos themselves for all these oil companies often refer to sort of nature and flowers, and it's all very nice and everything. But of course, we all know what the effects of burning all these fossil fuels are in terms of how they've changed our environment. So, I don't want to project a simplistic idea that it's all just bad, because it's enabled us to be in this room. Basically, if we didn't have oil, none of us would be sitting in this room. We wouldn't be able to talk about this or anything. But also, we have to appreciate that it's a finite resource and it's fundamentally changing the planet. If you look at the per capita income of the largest multinational companies, until recently, when the tech companies started to become number one, this is from a couple of years ago, Apple was number one. But always the companies with the biggest per capita income are oil companies. So you get Exxon, PetroChina, Royal Dutch Shell, all of those ones that are listed there, are the companies that earn more money than any other company on earth. So this idea fascinated me. Also, the whole idea that oil actually originally came from plants that existed millions of years ago that no longer exists. So I took my software that I've shown you in earlier incarnations, and in the actual DNA of the system itself, I fed the information from the oil company logo. So I basically went online, found all the oil company logos, converted them into 3D models, broke the 3D models into their constituent parts, and used them as the fundamental basis for evolving these new platforms based on oil company logos. So this one was made from the BP logo. This one looks a bit like a Banksia, but it's actually made from the Esso logo. So if you look, unfortunately because the projector can't really show you, but these images are very, very high resolution. And if you really look very, very closely, you'll see that all of these are actually the O from the Esso logo, and inside is the S. And then there's other bits where the geometry has been mutated and distorted, and it doesn't actually look like the letter forms anymore, like these funny wings that emerged around the branches of the tree, and so on. This is the 76 logo that somehow became hairy. The old BP logo as well. So I ended up evolving 50 of these, and they were exhibited at the museum in Austria. They're all 1 by 1 metre square. There's 50 different ones, all based on a different oil company logo. That's Church of the Wall in New Zealand where they were putting them up. Just coincidentally, another big plug, but this work is up for the Lumen Prize. So if you go to the Lumen Prize website, you can vote for it if you want to. Not that I would ask you to do that unnecessarily. Also at Monash we have this incredible data visualization platform called the Cave 2. Do people know about this? It's like going to Harvey Norman but for data visualization. It's a whole lot of LCD. That is a bit weird. It's worth quite a lot of money. It's very impressive when you go in there, but it's a whole lot of LCD panels that work in stereo, so you can put on 3D glasses and you can sort of be in this very immersive space. So when the Cave was first purchased, I redid the work for there. And the great thing about that was because the screens are such high resolution, you could walk right up and see the detail that's in it. So at first glance you might look at it and think that looks like some weird science fiction plant. So this work was shown at ACME in Melbourne, 2004, I think. And I've exhibited it quite a lot all over the world. It always amazes me when I run it what it actually ends up doing. Even though the visual appearance is consistently the same, the behaviour of the creatures was really fascinating. So they would learn to do things like hibernate in the winter, because there are seasons, like summer, autumn, winter, spring. And in the winter when food is scarce, they would learn to hibernate. They would also learn to communicate with one another, to warn of predators approaching and things. And none of this is programmed into the simulation. They learn it through this evolutionary process. I'll show you a video. Just turn the volume down a little bit. It's very hard to see from the video what's actually going on, like what's food and what's a creature, because unfortunately the video doesn't bring it out too well. But basically lots of the circles are food. The things that are flashing are the creatures that are eating the food. By connecting the presence of people in the space with the supply of food, the creatures try to attract people by making interesting sounds, because if you're interested in the work, you'll spend longer there, and that will provide the creatures with more food. So even though they have no knowledge there are people in the environment, they learn through evolution that by making interesting sounds and keeping people in the space for longer, then they can increase their chances of survival and reproduction. So hence they evolve to make interesting sounds. So not the sounds that I programmed them to make, the sounds that they learnt to evolve. Okay, running out of time, so I'll move forward quite quickly. I sort of took this idea a bit further, again for another work in Ars Electronica, in their big deep space visualization system, which is basically, they've got lots of money. So they have, now they're 8K projectors, but at the time when I was there, they were only 4K projectors in a big stereoscopic immersive wall. It's basically a zoological connection of creatures that are tied to the ticket that you get. So you scan your ticket when you go in, and that's the DNA for the creature that you've generated. You can come back in later and see the evolutionary heritage of that creature. Okay, I'll skip some of the technical details. If anyone was really interested in this, I can talk about it later. But Another project that I've been working on more recently is this idea, it's called niche construction. It's basically a biological theory that animals create heritable environments for their offspring, and that they do that by changing environmental conditions locally to them. So the classic example is the beaver's dam. You know, the beaver takes a whole lot of materials and blocks the dam to make an environment that's suitable for it in its offspring. I took this idea and tried to make line drawing programs that just did this very simply. This video shows how they work. They have genes. The genes control their behaviour, but they also have a propensity for a certain density. So some of the creatures like high density with lots of lines, some like low density with just a few lines. So they learn to make patterns that suit their environmental niche, the density that they like. And what this gives you is these really complex drawings. So this is just showing you, like every time you run the program, you get something different. You get something that's quite interesting. Some of the ones that like high density, obviously you're drawing these things. Some that like low density evolve strategies like creating a big area and closing it off to other ones. Because I didn't mention that there's a rule that says if you intersect with the line drawn by another creature, then you die. So that's basically what you see are the drawings that are made over an evolutionary epoch, and all of the creatures become extinct eventually because they find they've got nowhere left to go. So these are just a couple of examples of the drawings. What's fascinating to me about this is that every time you run the program, you get a completely different drawing in terms of the way, the style of it, the complexity, and so on. So the latest version of this work is actually taking it from a software version to a robot version. So last year I was invited to ICHCAI, which is a big AI conference. It was in Argentina, and had this exhibition of drawing robots. Because I'm running out of time, I'll click through these and show you the video. So I basically took the software and created robots that have a niche preference for drawing at a particular density. And these, the robots just have pens attached to them. They're autonomous in the sense that there's nothing controlling them. They're just deciding by looking at the patterns of lines. They've got sensors that can detect the lines, what they're drawing. So over a long period of time, they create these very complex drawings on a 4x4 metre piece of paper. And each one, again, is like the software versions. It's different. It's not the same style because obviously they can't evolve, like they can't reproduce and give birth to children and all that kind of thing like the software versions can. So they're fixed in terms of their evolutionary behaviour. But they still manage to produce through this interaction with their environment these drawings that would remind you of something that insects might do or something like that. And indeed, many years ago, I attended a workshop on wasp behaviour because I was interested in that. And some of the people presented these drawings showing the patterns that wasps make in their paths to and from their nests. And they don't look exactly like this, but they do have this sort of uncanny resemblance to something that would look like, if you saw it in an art gallery, you'd go, yeah, that's great art, I'd really like to see that, but it was just made by wasps. So I'm trying to achieve the same thing here by creating these robots that draw these complex drawings, but through this bottom-up emergent process. Just very quickly to finish, a couple of recent works that deal with sound sonification, I guess. This work was recently shown in Sydney. It's a collaboration with Gary Warner, an artist who I've worked with for many years. It consists of a whole series of audio recordings from the Macaulay Library. It's based at Cornell University. It's basically recordings of people recording the sounds of nature, but we removed the natural sounds and just recorded the sounds of people annotating into the microphone. It's a generative piece in the sense that each speaker, there's 16 speakers in this dome, it's in real time playing back the samples according to an algorithm that's run on a Raspberry Pi computer written in JavaScript for those technically minded. And so it creates this kind of infusion of multi-channel sound about the environments that these biologists were recording the sound of nature, much of which is now no longer in existence. Okay, because I've run out of time, I might leave it there. But this is just one more work, colour field, that is basically an evolutionary ecosystem of colour. So there's a whole lot of agents that represent a certain colour, and over evolutionary time, they change the patterns that they create, creating this sort of very complex range of colours that harmonise with each other, and then basically they decide that they don't like each other anymore, so it goes into this chaotic state and reconfigures. I mean, the thing that all these works have in common is this generative complexity, and also that, for me, it's interesting for me to look. I mean, often when you work as an artist, you kind of get bored of looking at your own work, but these systems are systems, they're not static works, and they have a fascination in themselves that comes from the fact that the computer is playing a big part in the creative process, and that's what I really like. Just another quick plug. If you're interested in learning about this stuff, we run a free online course in creative coding. It's running at the moment. It's not too late to join. You can watch endless videos of me talking and other people as well, if you're really that inclined. And we cover a lot of these things, not in huge amounts of detail, but in enough so that you can start coding them yourself and learn a bit more about them. And it's a free course, so what's not to like? If you're interested in finding out more, a couple of books that I've written, website, contact information. Thank you very much.
So we have 5 minutes, maybe 2 or 3 questions for John.
When you create your models, how do you parameterize them? For example, the logos that you have, how do you go about taking that logo and putting it into your program?
So I got the original vector files for the logo, made them into 3D models, then broke them up into their graphic elements. So if you take like the BP logo, the new one has a whole lot of little flower shapes. So they're the basic primitives. So they just all get sort of thrown into the system, and it works out how to reassemble them and how to change them.
So is the first step then trying to reproduce the logo of your program? So it's reproducing and then it knows what it did and tries to do anything? Yes.
So each of the files that generate the images is like just one page of this code, but it looks like gobbledygook to even me. I mean, I understand parts of it, but it's very cryptic. And so a lot of the time is spent. I have a whole series of processes. Some of them are evolutionary, some of the equivalent of like gene splicing. So you get one good bit and you splice it with another gene that does another good bit, and they kind of join together. One thing that's really fascinating is that, I mean, if you know about biology, you might have heard the term junk DNA, like all those sections of DNA that apparently people first thought had no purpose, but it turns out that they do. You get the equivalent of that. You get a whole lot of motifs or forms that disappear, they're bred out, but they're actually still there. But the DNA is actually jumping over them and not using them. But then you go through mutation and suddenly they come back in some other weird form because they've undergone mutation. And that's like fantastic, because you go, oh, I forgot about that. That was 18,000 generations ago, and now look, it's suddenly come back into the picture, and it surprises you that suddenly this weird thing that you thought had gone was still there all the time, just hiding away, and hasn't revealed itself until later. Yeah, I mean, I make it sound like it's easy, right? But it's I do spend a lot of time with stuff that I don't show you. What is easy to do? Yes.
One thing which I'm really interested about with this is there's this sort of balance of design and emergence.
Yeah.
And I'm really interested to hear your thoughts on finding that balance and balancing those two competing concerns of wanting to design the outcome and also allowing the emergent behaviour to.
Yeah, that's a really good question, and it's actually a really deep question in a sense of designing the software itself. I mean, I guess they're presented as artwork, so you have, and they're presented as your artwork. So it's not. I've never written anything in the sense that I just write it, stand back, and whatever happens, I'm going to exhibit. There's a lot of editing and changing, and you don't start with a piece of software and finish with the same piece of software. You work out what works, what doesn't work. So in the sense, there's a lot of manipulation that happens, but also there's a lot of surprise and serendipity and those kinds of things. So you do try. I mean, there's obviously an aesthetic that's present in my work, which comes from me, because if other people were to use the same techniques, they'd come up with something different. So it's not like the machine is completely autonomous and it's making all decisions and all designs. There is that balance, and I guess that's that's really the nub of the problem, is how do you have a system that really you want to not have control over, and yet you do want to have control over it. It's a beautiful conundrum, in the sense that you want to have that balance between lack of control, surprise, things that amaze you that you didn't think of, but things that you still find interesting, find stimulating, and find exciting. Because a lot of the stuff that it will produce is not stimulating, interesting, or exciting. It's dead boring, or wrong, or stupid, or bad. So that's the challenge in working in this area, I guess, is to solve that problem.
There's a guy called Wolfram.
Yes, he's still alive. Yeah.
Talked about that too.
Yes.
Was that got a similarity to what you were doing here?
In a sense, I mean, there's lots of people who've studied these systems in general. I mean, Stephen Wolfram he's quite famous, I guess, because he worked in physics, and he wrote a piece of software that helped people do physics and then later on do a whole lot of scientific inquiry. And the book that you're referring to was called A New Kind of Science. You can read the reviews online. Not everyone would agree that it was a new kind of science or that he invented it, which is not the case. But certainly, this spans a whole lot of disciplines. In the 50s there was systems theory, where people started to look at systems in general and say, well, why is it that this system from biology is like this system from somewhere else? And that fell out of favour later on, but it's undergone resurgences and so on. And often, the thing is that basically there are these fundamentally interesting things in mathematics and computing that generate this complexity, and no one really understands exactly why they do it or how they do it. The only way to understand is to actually empirically test them, to write the software and make them generate those things. So it's sort of kind of
parallel between stuff I read in some of the
yeah. So he certainly looks at a lot of the systems. I mean, one thing that's great about that book is that it's got hundreds of examples of really interesting systems. Yeah.
Okay, thank you, and let's put our hands together for John as well.